Okay, good morning, everybody. At least for me and those from the custom team. Okay, Carlos here. I'm just a little bit of context. I'm a co-founder of a company called Beta Robots, placed here in Spain. And my expertise used to be in robotic manipulation, but I would say now that I try to be, I try to span any area of interest related to real problem solving. So first of all, I think you might agree with me that simulating a robotic system is not as common as we want it to be in robotic development. And it's sometimes it's because it's not easy to model and it's not easy to, how do you say, to identify whatever you see in reality with and match it with the simulation. But I think it has several advantages that to simulate robotic systems, and it's that you can, for instance, as you can see in the use cases, for instance, safety check. That is any change of your code. You can test any change on your algorithm and without breaking anything. I think that's everything that everyone has to wants to have it. Quality checked. For instance, you already have some performances of your code, and you want to check if your code, any change in your code base has effect to on the production cycle or whatever key feature you want to test. I think Luca already in some conferences before he talked about this functionality test. Well, this time we got to see him with the PSL filters. Another use case is, for instance, generating data to feed machine learning knowledge. For instance, just to create contact-based, for instance, in manipulation, I have seen works feeding contact data into machine learning so they can perform more robust grasps. Another use case is, for instance, aiding the mechanical design of any robot. Like, for instance, there was an example of a master student who wanted to test his idea about an helix driving a car. So before building everything, he wanted to test if that even worked. So he tried first simulating everything in Gazebo, and then he got to build the design. Another thing is, for instance, you want to develop algorithms in remote without having the need. Sorry, here I missed without having the need of the real actual robot. For instance, you are traveling and you want to test this idea of a new algorithm, and you can develop in remote and then come back to the lab and test it. And nowadays, it's also a support for selling. For instance, you can see simulations in advertisements. So, for instance, it's I was just posting this example that if you see two advertisements of a bouncing ball, and you see that it's very programmatically falling down, and you see another with a physical, feasible, plausible simulation, I would bet that you choose the one with a more physical, plausible simulation than the other one, because you see this is more serious, right? So what I'm going to talk about today is, but I just want to share some tips and ideas that I crossed by developing several projects, and in particular this chess lab. And it's about how to set up different robots in simulation using ros-control and the Gazebo ros-control plugin. How to use and create custom Gazebo ROS plugins. How to optimize the simulation and from the model point of view, basically collision, geometries, and more tips and ideas about namespaces and launch files. So the chess lab, this is combined work by me and and Professor Jean Roussel at the Polytechnical University of Catalonia. This is what we gave to the master students so they can develop inverse kinematic algorithms, try chess moves, and these kind of things. Basically, there is a chessboard with some parts. This is a very basic. We didn't want to create complex object perception, so we relied on aruco markers and 2 cameras and 2 universal robot arms equipped with the robotic grippers. So we're not gonna try any cameras today, but we're gonna share more of how everything is set up. So the main package you will find is this, like the integrating package is the chess lab setup. There you can find, for instance, configuration, launch files, model files. It's the one that integrates everything, right? So this is one of the first steps. I know there are several ways to do things. So from my short but intense experience with ROS is I came to the conclusion that it's really nice to have this like a main launch file where you have all the modules that you want to use, and you want to set you want to have different set of parameter of arguments to launch each module or the other one. So this is like your library, and the idea from the beginning was to have as much modularity as possible. For instance, I want to launch only the arms. I want to launch only the right arm or the left arm. I want to launch only the cameras, test everything. So just having one main launch file, the XML extension is just to avoid the auto-completion from the terminal. From there, you want to have a set of parameters of arguments that you can have in the handy way in other launch files that include that one, right? So let's try to do this. I'm gonna go for the shell. I like to try always the classical way. So we're gonna try ROS Launch Chess Lab just to try that everything works, just without the cameras. And I'm gonna open here the Gazebo client. Let's put it a little bit big. So it's gonna start. You will see some errors here, but it's about the GUI. So you know that in ROS.ds there is not GUI. You have to open it in a separate window. You will see also some errors about the PID gains not set up. I just decided to go for the only position control of the arms in simulation as well. So what you see here is just the simulations. If you want to test, I just gave you here a small script where you configure the 2 clients, action clients for the trajectory controller. I assume you are more or less familiar with this. Basically, there is an action, follow your trajectory action. So you set the 2 clients, and in this case, I'm using 2 waypoints, and then I configure the goals, and then I send asynchronously the 2 goals. So and I just wait for the 2 of them to finalize the trajectory. So if you run this, you should see I opened the beginner account, sorry. You should see the 2 arms moving at some point. So it's just running. You should see it running without problems. So while it's loading the algorithm, I just want to mention that I would say that the main issues for the simulations to become more mainstream are basically you want to write zero additional code, because one of the most typical answers when I try to encourage the use of simulation to test algorithms is, oh, but I can try with the robot faster. Okay, so that sometimes makes sense, but then that's something that we need to improve on from the simulation side. It's that you don't want to. Wait, I'm gonna interrupt. Let's start again. You want to. That's something that we need to work on. That in from the simulation point of view, we need to add more generic code and plugins. So we write zero code, but more configuration side, so it's easier to simulate robots. Okay, there you go. I don't know if you catch what I did. I just interrupted the kernel because maybe it was from a previous ROS session, and then I restarted, and then I run it again. So the node connected again with the ROS master. So before going, let me finish the issues that I think are important to make the simulations more mainstream. So I was telling you about the zero additional code. Another thing is as in any other modeling of system, you want a minimal representation that does not compromise functionality. That's important that you have that in mind. Another thing is perhaps you want to have a virtualized environment that where you have all the simulation-wise dependencies and not in your local system. For instance, in this case, ROS-DS is a great alternative. You want to also switch between real scenario and simulated scenario, and you want that switch to be as transparent as possible. So, because we all know that duplicating launch files or topic remaps, that can be sources of silly errors that can make you mad in a big project. Like you're trying to figure out what's happening, and it's a remap from some included launch file that you didn't have in mind, right? So I'm gonna share these ideas that try to tackle or handle these issues that I just mentioned. So the first thing is Gazebo ros-control plugin, which is very famous and common because it tackles the zero additional code that you need to write because someone already wrote very nice. Sorry, let me just stop that. Zero additional code. Someone already wrote this great plugin that creates a hardware interface for any robot in simulation. It's basically creating your hardware abstraction layer, but already talking to the simulation. So this person already took care of communicating with the Gazebo API. So the thing is, this plugin is it's a model plugin. Sorry, this plugin is a model plugin, right? So if you want to have this switch between real scenario and simulated scenario very smooth, you want to have the topics coming from the simulation the same as in the real scenario, right? So a very common use case is to have a gripper mounted on an arm, right? So in this case, I have a universal robot arm, which is a brand, and you have another brand, which is Robotic gripper. It's different from the previous speech where they had all dynamic cell models, so they can share the same. I guess I have no experience with dynamic cell, but I guess they have a single hardware abstraction layer that it's for them it's no problem. But sometimes you have to integrate two brands of robots, right? So in this case, you want the gripper to be mounted on the arm, but then you want the topics coming from the arm different from the topic coming from the arm, from the gripper, right? So in this case, what I did is just to have a separate URDF file for the arm. This is what it looks like. For instance, I attach this is the macro coming from the that instantiates the robotic model, the arm model coming from this include, and I attach it to the world at some configuration. And in this case, I added the gazebo plugin here with the namespace of the arm that's going to be running also in the real scenario. I just want to note here that this UR description package is the one from ROSALES. It's not exactly the same as the ROSALES, because in that package, the plugin is added by default, and they didn't parameterize the namespace. So I just wanted to see clearly what I'm adding into the URDF file. And in the case of the gripper, I just did something interesting. Every time I find something interesting in a new project, I just wanted to have this in a separate file as well. So what I did with the robotic gripper is to use the root link of the gripper, as the last link of the robotic arm. In this way, the robot state publisher will parse this and publish the TF frame, and will attach. You will see in RVs always the robotic gripper attached to the arm. So what I do is in simulation, I spawn both files as a separate models. So in Gazebo, if you use the world name as a root link, it will make your model static in Gazebo. So in this case, the gripper will not be static. In this case, it will just fall, as you might think. So you might think this as you want to screw your gripper, as in the real life, to the robot, right? So in order for this to actually move, I just needed something in the world view that screw this together, right? And that's where this custom plugin comes up. So in this case, I just needed a word plugin, not a model plugin, because it needs to be aware of the two models already spawned in simulation, right? So I just found some Gazebo ROS attaching plugin and just made it custom, because I wanted to screw the gripper at a specific position of the arm. And in that case, it wasn't like that. So this is what it looks like when you just add the plugin in your Word file, because in this case you don't add it into the URDF, you add it into the Word file because it's a Word plugin, right? So this is basically the solution of the forward kinematics of the arm at the starting position. Of course, if you change the home position or the starting position of the arm when you load the simulation, it will attach the gripper in any other place, and it will move according to the robot, but in an offset position, right? Okay, that's more or less what I wanted to show you about the hardware abstraction in Gazebo and also in the real life. You need to later on I will show you the launch file the part of the launch file corresponding to the real arm. So you will see that this namespace is the same as sorry. You will see that this namespace here is the same of the one that I'm launching the real driver and the controllers. So the topics and the actions will be exactly the same in simulation and in real life. So what about modeling? It's very common And it's a very common lazy practice. I include myself because I have done it before as well. And you saw already from the previous talk, also they were using SolidWorks to generate the visual geometry. But it's very common to also use the same visual geometry for the collision geometry, which it's not always the best. I mean, it will depend on the purpose of the simulation, of course. If you want to generate data for machine learning algorithms according to the context and how the context evolved, then you need to have a precise mesh of the gripper. But it's not always the same. So in this case, you see that I have a very simplified version of the gripper and also of the UR. Again, this is a modified version of the UR description. This is not as gross AI you will find. I just added a precise collision parameter on the URDF. It's by default it uses the mesh, so I guess if it's interesting upstream, I might add it. I may add pull request or something. But from my experience, I try, if you are familiar with Move It, for instance, and you want to practice and you want to test the collision check of this model is 10 times faster than if you use the precise geometry. And for some application, this is already enough. So so it's up to you to dedicate maybe one morning to generate the basic collision geometry of your robot using. You see here there are some meshes, but this is actually how RVs renders a cylinder. But in the collision engine of Gazebo, it's using a primitive called a cylinder, which is easier to check for collisions, right? Okay, that's basically, and the same goes for, I mean, this is just something that you can do very quickly, and it doesn't require identifying, for instance, friction or damping of your joints, which is also more inconvenient, and the default values sometimes are enough as well. Okay, let's continue then. Regarding the launches and namespaces. As in any programming environment, ROS has several ways to do the same thing as always. And some people might think this is pro, or this is good, or this is bad. For instance, if you have programmed in Python, you know there is a mandatory syntaxes that if you don't follow it, the code doesn't work. So sometimes this is good, this is bad. Okay, in my opinion, is I think it's good to have several ways to do the same thing. So, as I told you, from several projects, I have developed several ways to do the launch files, and I found this main launch scheme to be very useful. So this is what it looks like. For instance, this is just the namespace of the team A. For instance, this is like the right arm. And to be as modular as possible, this is something that you might think when you start programming in ROS, you think that the robot description is untouchable. That's the holy parameter of robot thing. So and the pair also with the joint state publisher and the robot state publisher, which builds up the TF tree. They have to be running always on the global namespace, which is not entirely true. That's the ROS people, the programming the infrastructure. They are very smart, and they do this in a very smart way that you can flex this into your work scheme. So this is the first time I tried like this namespaces with the robot description parameter. I usually have also namespaces, but I send everything then to the global namespace. And in this case, I don't have the global robot description or the global join states. So everything is inside a group. Each robot, each piece of hardware, I mean the one robot, the other robot, the gripper, the other gripper, and one camera and the other camera. If you explore into the code, they have their own group, which I can enable or not from outside, and they all run inside their own namespace. All right. So this is what I was telling you about. This is the part of the real driver. This is the same hardware abstraction, the same library using the hardware to generate the hardware abstraction layer is ros-controls. Here are the controllers. This is where you load. All right. Double click. This is where you load the joint trajectory. So and this is okay. You can follow also the rights. There is something interesting here that the joint trajectory controller also has a RQT plugin. And I was looking at the plugin, and it loads the robot description to parse the information for the joint limits and this kind of information that you need to create the sliders. So I couldn't find a way to change to remap the parameter for the joint for this plugin. So what I did is just to put it inside the namespace, and that in that way you can test the connectivity with the robot or with the simulation, so you can move the joint, each joint separately. So before coming into the last point, I just want to, in your projects, everything is on a Git repository. So this is, if you go into the Captain workspace, let me put this a little bit bigger. Everything is in a Git repository. So if you Git status, you will see all the things. So if you continuously perform Git pull and Git to module update, Git pull and Git to module update, this is like a meta. This is Git issue. This is I used to work also with several modules on Git, but then I use submodules, Git submodules to have all the modules that I want for that particular project. So if you perform Git submodule update, you will update all the submodules at the current commit that the meta project is pointing at. So I just want to show you this, and also for instance, there is I won't show a demo, but here you have also analytic solution of the inverse kinematic. Remember, this is in the academic purpose, so we teach also kinematics in the master. So there is a package that already have the analytic solution for the UR3 arm. Right? It's just nothing complex, but there is also already a service server that you can call from any other node and perform the inverse kinematics, so you can move the robot into, at the specific pose of the end effector. All right, just wanted to show you that. Also, I think there is also the notebook. Is also, you have the ROSALES type, so I will try to amend all these typos that I found, and so if you get pulled at some point in the week, it will update. But it has it's private, but I will make it public. All right. So your project will be also evolving in time. I think that's kind of cool from the teaching purpose. So about the matching virtualization, I have so little to say. I just think that basically you have options like 2 PCs. You can set one PC with all the simulation dependencies. So you don't want to put noise in, or more dependencies on your own computer. It costs money and time, of course, and you can set the two PC, the ROS network in two PCs, and that's feasible. Another thing is you can have only one PC, and you can run a Docker images with your simulation and all the dependencies of your simulations on a virtual in a container. But it costs a lot of time if you don't know Docker, which is, for instance, my case. I just use Docker for continuous integration and testing building, but not running programs inside and these kind of things. And of course, the last alternative is if you can have a one PC and ROS Development Studio to test your simulations, where I hope you enjoy as much as I did.